So we're going to talk about torque now. And specifically, let's go ahead and define torque, and then we'll draw some examples and give some different examples to try to help you understand what torque is. So torque is a twisting force over a specific length. So a twisting force over a specific length, which means that for torque, you're going to be twisting something. So it's going to be going in a circular motion. So a perfect example of this, see if I can draw it, would be a wrench. Again, excuse my drawing skills. There we go. So here's a wrench. And so the idea is you have some sort of nut that's right here, or bolt, that you're trying to turn, and you are applying a force, a twisting force, along a specific length. And here, the length is the length of the lever, or the length of the wrench. We're going to be talking about levers. And so a lever is just a type of simple machine. And it's specifically dealing with this torque idea. So levers are anything where you're twisting it in this direction. You're pushing down on one side, which causes a turning in the middle. So another example would be the classic, you've got some sort of base here, and then you've got a ramp or a long board, and you are pushing down on this board in order to lift a box or crate or something like that. So this is also a lever because you're pushing something down in order to lift something up over here. So again, it's got this twisting motion going on, this circular motion. So torque is just applying a force along a lever in a specific length. So for torque, the equation for torque is tau, which is just a little t with like a little tail on the end, so capital T with a tail, equals force, right, because it's a twisting force, times the distance, because it's a length, of the lever. So torque is the force applied times the distance along the lever, or the length of the lever. So this is our equation we're going to be using. So my next question is, let's talk about doors. If you've seen Lord of the Rings, you know hobbits have very interesting houses. So this is a hobbit house, and you should notice that the front door first is circular, which is really odd. But secondly, if you look really closely, the doorknob for a hobbit door is in the very center of the door. Here, we have our hinges on this side, in a standard door, and our handle is on the opposite end. So one reason why we don't have doors like this is because they'd be very expensive to make, because all of the mechanisms that are here would have to extend all the way to halfway through the door. The other reason why we don't is because of this whole torque idea. You want the longest distance possible, so you have to apply less force. So again, torque is force times the lever arm. So to apply a certain amount of torque, if you have a longer lever arm, then you apply less force. If you have a shorter lever arm, you have to apply more force. And so anyone who has ever worked with tools, you know that if you are really trying to tighten down a nut or a bolt, then you want a long wrench. The shorter the wrench is, the harder it is to really tighten things down. So for the door example here, you want as long of a distance as possible, so you only have to apply a little bit of force to get the door to pivot open. If you've ever gone shopping and accidentally pushed on the hinge side of the door, you know it's very hard to push the door open from this side as it is from this side. And that's because at this point, this is your distance. You have a teeny tiny distance. So in order to get this door to open, you have to apply a large force over a small distance, whereas if you push from the other end, then you have a long distance, which means you only have to apply a small force. Okay, so the force and distance are inversely related. Okay, so force and distance are inversely related. So the other thing you're going to be required to do is actually calculate some torques. So here we go. It's as simple as it seems. Torque is equal to force times the distance on the lever arm. So a force of 10 newtons is applied on a 0.3 meter handle. And so we just multiply those together and we get 3. The units for torque are literally putting these two units together. So it's 3 Newton meters, and you're done. In the standard units, so again, those of you that have worked with tools, you know the torque measurements. Here it's Newton meters, which is a measure of force and a measure of distance. In the standard unit, which you will not use in here at all, but just for completion's sake, it's foot-pounds of torque. So foot-pounds, where feet measures a distance and pounds measures a force. So foot-pounds and Newton meters. All right, so our next example says what maximum force can be applied on a 40 Newton meter torque wrench that is 0.4 meters long. So now we know the torque, so we'll put that over here. And we know the distance, we're looking for the force. So for this one, we're going to divide by 0.4, and we get a force of 100 newtons. So you can apply 100 newtons of force on this torque wrench. The other type of examples you're going to have to worry about are seesaw examples. So for seesaw examples, this is the classic children's toy out on playgrounds, but they don't really exist anymore, which is kind of sad, of where you've got this seesaw, and you've got one person sitting over here, and then you've got one person sitting over here, and you're going up and down. And so we can see torque here as well. This is the pivot point. This is where the seesaw is attached. And so we have a certain length. Here we go. So this is your distance. And then the force that's applied is actually the weight of the child for the most part. So the weight of the child is your force, and then the distance from that pivot point is your distance. So for example, let's say we have kids of equal weights and they're located equal distance. Well, then they'll have a really good time on the seesaw because we have an equal force, equal distance, equal force, equal distance. So everything is nice and equal. They'll just go up and down and up and down. But what if, for example, we had a seesaw where we had an adult sitting with a small child. So now we have a much larger force here than we do here because of their weight differences, but they're sitting the same distance apart. So now this side has a large force with a certain distance, and this side has a small force with the same distance. So what's going to happen here is there's more torque on this end than there is on this end. And so anyone who's been this person knows it's not very fun because you keep getting flown up in the air. The person on this side knows it's no fun because you keep getting your butt smacked on the ground because there's just not enough force over here to bounce you back up. And so either way, this is not any fun. So the question is how can we fix this? So what could this parent do to make it to where both of them could have fun, where he could have fun with his kid or she could have fun with her kid? And so what we're going to do is, since we can't change the weight, I mean, you can't just sit there and wait for your kid to get to the same weight as you, but what we can do is we can adjust where we sit. So if we have a little force, right, little force, we need a big distance. So we're going to have our kid sit on the very end of the seesaw. So we have a little force and a big distance. For our parent, we have a large force, so we're going to need a little distance. So we're going to have him or her sit much closer to the pivot point. So this is a big force with a little distance. And so large force with little distance will equal the little force with the large distance. And now they will have equal ups and downs. And so both of them can have lots of fun again. So how do we do this mathematically? Well, it's right here. It's the idea that the torque on one side of your pivot point is going to be equal to the torque on the other side of your pivot point. That's whenever everything is nice and equal and you can actually have a good time on a seesaw. So let's do a couple of examples there. So how far should a 10 Newton object be placed? So how far should the 10 Newton object be to balance an 8 Newton object at 0.7 meters from the fulcrum? So we have a distance that we need to find with a force, and then we have another force with a distance. So our equation again is torque. Torque equals force times the distance of the lever. And so on one side we have D, or we're given F, so 10 times D. And that torque is going to be equal to the other torque. So 8 times 0.7. So we have 10D equals, and that would be 5.6. And so then we're going to divide by 10. And we get a distance of 0.56. And our unit here is meters, so this will also be meters. Because these are being set equal to each other, whatever this unit is, this one has to be in the same unit. But you can have this in newtons, have them both in newtons. You can have them both in kilonewtons. You can have them both in kilograms. But as long as they're in the same unit, you're okay. Same thing for distance. These can both be in meters. They can both be in centimeters. They can both be in kilometers. It doesn't matter as long as they're the same. If you're doing just a straight up example, like here, force has to be in newtons and the distance has to be in meters because you need that unit of Newton meters. So for example here, we have a 6 Newton object and we're looking for what length, and then our other object is a 4 Newton object that's 15 centimeters. Now we do not have to convert this. We can just use it in centimeters. And here's how. We have 6 newtons times our distance, And that's going to be equal to our 4 newtons times our 15 centimeters. So we have 6D equals 4 times 15 is 60. And so then we're going to divide by 6. And we get a distance of 10. Because this is in centimeters, this one will also be in centimeters. And that's it.